something that we'll call a weight. So the weight is something like the cost of this edge. Okay? And so let me describe the problem and then I'll tell you where this comes up. So a subgraph of G is just a subset of edges, right? So it's like I get some subset of these edges. A subgraph spans G if it satisfies the two properties that, so the subgraph is connected, okay, and two, all vertices of G are in the subgraph. So it's like, for example, if I've got a bunch of vertices here, like I want to have something like that's a spanning subgraph because all the vertices are participating in this. There could be more edges in the graph, but I'm not choosing those. I'm just choosing a subset that spans. And the problem is to find a spanning subgraph of minimum weight. Okay? Where the weight of a subgraph is just the weight of the edges. Clear? Yeah?
Like, let me rephrase it so.
Yeah?
It's like to get that same number of edges.
Not the.
In that case, but number of vertices, but finding the best way to connect between the existing edges.
Yeah. That's kind of, yeah. So the where this pops up is, I mean, so actually think of it as, suppose you have an internet service provider, right, who has to provide connectivity to all these places. But to lay cable between two places costs them something. So what is the minimum amount of cable they need to lay so that everybody can get to everyone through those cables? Does that make sense? And so, by the way, something that just, we're so used to the digital world, we forget that a lot of it is fundamentally physical. Like, internet basically goes through cable, right? It's actually wire. I mean, with Starlink, they're trying to do it with satellites, but by and large, it's wire. So there's actually a wire that goes across the Atlantic Ocean. There's some thick, fat cable that someone has laid. So can you imagine how they actually laid that cable? Like, that's crazy, right? They must have actually loaded all that cable onto a ship and taken that ship and slowly dropped it as they went along. Yeah?
And they did it over like 100 years ago, too.
Yeah, for the telegraph, right? That's how the telegraph started. Yeah, which is like, I don't know, it's insane that they would have done that. So you have to lay cable everywhere for the internet to actually work. So there's cable that's going all across the world. Or even in the US for the power grid, that's how it works, right? All the power grids usually end up being connected, which is why sometimes a tree falls and half of New York loses power because some power line goes down. And so all of these companies that are building utilities often have to solve some version of this problem. Not exactly minimum spanning trees, but some version. Okay, so the problem is to find a spanning subgraph of minimum weight. Does this make sense? So the first observation that we make, that is a minimum weight spanning subgraph is a tree. Okay, so what does that mean? So what is a tree? A tree is a graph that contains no cycles. So why is the minimum weight spanning subgraph a tree? Why can you always do with just a tree?
Because
if you basically have a cycle, so I'm going to write this down. If you have a cycle in a spanning subgraph, you can remove any edge of the cycle and it's still going to be a spanning subgraph. Right? So I'll just write this down as a claim. And this is going to be very important for how we're going to come up with minimum spanning trees. Consider a spanning subgraph that I'm going to call F. So what is a spanning subgraph? It's just a subset of the edges. Right? So I took my graph, and then there are a bunch of edges that I picked. So there are some edges that I've picked. Suppose F contains a cycle C. So here's a cycle. There's a cycle. If we remove any edge of the cycle, any edge E of the cycle, I'll say F set minus E. Right? This means I just removed E from the set. If I remove this edge, this is also a spanning subgraph. I should maybe say that these are all non-negative, just so that be precise. Otherwise, if things are negative, then you would just take everything. So there, all the weights are non-negative because it's like a cost. It's how much you have to pay to build an edge. Okay. So if you remove any edge E of the cycle, then F minus E is also a spanning subgraph. And I'll just write down the short proof. The idea is simply that when you remove an edge of a cycle, you don't affect the connectivity properties. Because whatever edge was between those, there's still another path that goes between them. Right? So if there was any other path that was using that edge, it could also use that cycle to go through. Yeah? So I'll just write this down. The proof is, consider the edge E equals UV. So there is a path from U to V without edge E, and this is because there is a cycle. There is a cycle with E. Right? So because there's a cycle, there is this other path. This other path over here from U to V. So any path connecting vertices X and Y using E can be rerouted to create a path from X to Y without E. What this means is, suppose there was some path from X to Y that used E. I could also go here, take that cycle, and go to Y. Right? So I can always, if I have any path connecting vertices X and Y, I can construct another path that goes from X to Y without that edge, which means I can always avoid that edge if I need to. So if I remove that edge, the connectivity properties have not changed. Whatever was connected before is still connected. Does that make sense? So on removing E, all vertices or all pairs of vertices that were connected remain connected, right? And that's the argument. It's a pretty simple argument. I mean, I've been verbose just because I wanted to write it out. But is that clear? So what this says is, like, if there's an edge, and if there's any path that was using that edge, there's also a path that doesn't use that edge, which basically has the same endpoints. So on removing that edge, you still have a spanning subgraph. And so from this claim, the observation becomes kind of obvious, because if you have any cycle, you can always remove something and make it cheaper. So every time you have a cycle, you just keep removing edges. And if you keep removing edges and there's no cycle left, you end up with a tree. Right? And that's why this problem is called minimum spanning trees. Okay? So before before I write down the algorithm, let's just think about, and because we're talking about greedy, how would you start this? Like, if you wanted to construct, what is the first edge that you would buy? Yeah? Yeah.
My question is in the other graph, in your last graph, if you, no, the other one, the one with that, what happens if you remove the edge from X to U?
Sorry?
What happens if you remove the edge from X to U? So
if you remove an edge over there?
that would get everything unconnected. Well,
Unless that participated in a cycle.
so it means that
So all this is saying is,
leaves.
if you remove an edge of a cycle, things are still fine.
And how do you define if it participates in the cycle?
Yeah, okay, so this isn't giving an algorithm. It's just a mathematical property. Now we need to convert that by an algorithm by solving that problem.
Well, so now a possible solution could be just start with a node and find the shortest path, the neighbor who have like
The cheapest edge. Cheapest edge, yeah.
Finish like all that tree and connect the last one with the cheapest one that forms a cycle, and then remove the most expensive.
Yeah, so you're going to have to do this back and forth. Right, so you're sort of on the right track. I mean, this is intuitively what you need to do. You had your hand up, yeah.
I was going to say instead of starting with a node, starting with find the cheapest edge first.
That would be even easier, right? Just start with the cheapest edge. You know that the cheapest edge has to be there. So why do you know the cheapest edge has to be there?
But just there isn't a constraint about the type of subgraph, because maybe a subgraph doesn't contain every node.
The rules of the game are these two. You have to get all vertices, right? Because that's so so you're right, the cheapest edge is going to be in the minimum spanning tree. Let's just assume that all the weights are different, just to keep things easy. Why? Yeah?
I assume because the goal of the problem is to minimize the sum of the weight of the edges, and we're discussing greedy approaches, and I think
Sure, but now that I've given you this property, can you make that argument formal? Yeah?
It would basically be that the nodes have to be connected somehow, and connecting them directly with the cheapest edge is the cheapest possible way to have them connected.
Yes, but maybe the other edges were helping connect other things. And so it's not clear that even though you made this cheapest choice, those other choices are a little bit more expensive, but then they connect a lot of other things. So why does this cheapest edge have to be there? Does that you understand what I'm saying? Like, there's some dependencies here, right? Because by connecting these two things with the cheapest edge, or by any other edge, you're also trying to get connectivity between other things. It is true, the cheapest edge is going to be in the minimum spanning tree, and one can make that argument formal, and you have to use this somehow. You had your hand up. No. Don't think of it algorithmically. I'm asking a mathematical question. Right? I'm not asking for an algorithm. I'm just saying, give me an argument why the cheapest edge has to be there. Yeah?
So if you assume that the cheapest edge is not in the graph.
Good. That's the way to start. Yes.
And you have a subgraph, f of the graph that connects all the nodes in the graph.
Yep.
And then you add the cheapest edge, then a cycle, and then if you remove the more expensive edge, then you have.
Exactly. Good. So that's the argument. 3 lines. Excellent. Right? So the argument is, suppose the cheapest edge was not there. Well, go ahead and add it in. You've probably created a cycle. You have created a cycle because there already was a path connecting those. And because this was the cheapest edge, you can remove any edge of the cycle, go and remove a more expensive edge, and things became cheaper. So this is a very simple argument, but it's a very powerful argument. It's a very simple statement. It's obvious once I write this down, like, yeah, of course that's true. What's the big deal in proving that? But you see, using that, you can now prove that the cheapest edge has to be there. And we'll see that just by building that argument further and further, we can actually just come up with a minimum spanning tree algorithm. Okay? So I'm going to write down this argument because this is very useful. You see, when you're right, you know you're right. You're like, this is the right answer. It becomes very clear. So I'm just going to write this claim. The cheapest edge is in some MST. By MST, I mean minimum spanning tree. Excuse me. Just to be precise, if there are multiple edges of the same weight, there can be multiple different minimum spanning trees. It's not necessarily unique. Like if all the edges had the same weight, then any tree would work. So that's why I'm saying that the cheapest edge is in some MST, meaning that it's always a safe choice. If you get the cheapest edge, you know that there's some minimum spanning tree you can build from there. So let's just do this argument. Let the cheapest edge be E. And suppose E is not on some MST T. So there's some tree let's add E to T. So this is T. I added this E. Now U and V, so E is equal to UV. U and V were connected in T. So by adding UV, there is a cycle C in T union E that includes, there is a cycle that includes E. Yes?
Is this saying that the cheapest edge is part of all minimum spanning trees?
Good question. No. It's saying it's in some minimum spanning tree. Because the reason why you cannot say all is because if all edges have the same weight, then they're all the cheapest edges. And it's not, then, you can take any tree. So it's not necessarily the case that that edge is going to be in every tree, but it's going to be in some tree. If all the weights were different, then that is true. It is true that it's in all minimum spanning trees. Yeah?
The word after so something adding.
By adding. Sorry. So by adding UV, there is a cycle, right? So we've created now a cycle, which you can see over here. You've created a cycle that includes E. By the previous claim, we can remove any edge in the cycle in C and keep things as a spanning subgraph. Right? And so all other edges in C have a, okay, so I initially was calling it a weight, now I'm calling it a cost. So let's just call it cost. Have cost at least the cost of E, right? Because E was the cheapest edge. We can remove any such edge E prime, and take, so I took T union E, and then I subtracted E prime. So I put in E and I removed E prime. This is a spanning subgraph. Containing E and has a total cost at most cost of T, which was the cost of the MST. So this new thing must be an MST as well, right? Because the cost could not have gone up. So the new spanning subgraph is an MST. I wrote this a bit more verbose than needed, just so that we have it down and just so that you see the entire argument, and if there are any doubts, it's easy to answer. So what am I saying? I'm saying the cheapest edge has to be in some MST. Why? Suppose it was not in some, there's some minimum spanning tree. What I'm going to do is I'm going to take it and I'm going to modify it to get another spanning tree, minimum spanning tree, which has the edge. So what do? I add the edge, it creates a cycle. Now I can take out any other edge from the cycle and delete that. Now, we don't know how to make this. This is not an algorithm, it's just a proof. It's just a mathematical argument that the cheapest edge is in some MST. But the utility of this is, at this point, the first choice becomes obvious. Like your internet service provider, the first thing they do is to just buy the cheapest edge. And this is now going back to your question on how do you know it's a greedy algorithm? This is like starting to look greedy, right? Because you just know what the first choice is. There's no table to be worked out. Okay, so now what? So we're here. I can look at all the edges. I can, let's say, sort the edges by weight. And I got the cheapest edge E. What's the next thing I do? Yeah?
You find theoretically the next cheapest.
Okay, all right, fair enough. And the next cheapest edge, right? I'll go ahead and put the next cheapest edge. So I'm just going to call this E1, which is the cheapest. And then you said you buy E2, which is the next cheapest edge. Then the next cheapest edge. Okay, so maybe the next cheapest edge is E3, and you say, okay, just keep doing this. So I get E4. All right, I think you might see where this is going. I buy E5, and then I buy the next cheapest edge. I buy E6. And maybe E6 is that. Now what?
Now we have a cycle.
Yeah, so what should I do? Yeah?
E6 is the most expensive, so we should just remove the most expensive edge from the cycle.
Right, so you decided to try E6, and you realize it's a cycle, so you don't add it. But now your algorithm is stuck, right? What do you do next?
Well,
No.
If that's the total number of vertices, we are done.
You're done, but suppose you're not.
If not, then take the next.
The next cheapest edge.
And the next and the next and the next until you connect every vertex.
And the argument is if every time you put in an edge, if it forms a cycle, then you shouldn't put that edge. Right? Now, one needs to argue that this is correct. Right now, all we did is we said the cheapest edge is in some MST, but you'll see that pretty much that same argument is going to tell you that the next cheapest edge is. Now, this is a little careful. Okay, so then you get the next edge, you get E7, and then maybe you get E8. And if E9 were to create a cycle, say don't buy that. Right? So what you've just discovered is Kruskal's algorithm for the minimum spanning tree. One has to figure out how to do the cycles and checking all of that, so that requires some work, yeah?
That's because if you're always buying the cheapest first, E9 is necessarily going to be more expensive
than what you've already bought so far. So it creates a cycle, but it is the most expensive edge of the cycle. So that's a redundant choice. Yeah, exactly. Okay, so this idea would be sort the edges by cost. Your running time is O of m log m. Keep adding edges in order unless the edge forms a cycle with the existing choices. Right? Yeah?
I'm just thinking another way of doing that without having to sort the edges. If you start with a random node
Yeah.
and start doing like a DFS, and then you add like the next node. If you
So suppose you have a node, how do you start?
You start with a random neighbor,
Okay.
and then that random neighbor with another random
Sure, you do DFS.
another, and then another, and there you find a cycle. So you remove the most expensive edge.
But maybe none of those edges should have been chosen.
Well, but every time you find a cycle, you remove the most expensive edge. And that could also...
So you're picking all the edges as you keep going. You find a cycle, you say, okay, delete the most expensive one. The problem is, like in the DFS, you might find some cycles, but there could be other cycles that the DFS did not discover. You have to do it in a systematic way to ensure, right? So there is a way of trying to do this without sorting the edges, if that's what you're trying to avoid, which is kind of like what you're doing. It's not exactly like DFS, it's more like Dijkstra, actually, you'll see. There's like yeah?
Can you repeat the expression that you gave?
So what I was saying was that, like, let's just say you're doing DFS and then you find a cycle, right? So maybe I should just draw this. Like you start here and you picked all these edges, you found a cycle. So you go look at the most expensive edge and you remove it. Now, you're going to do something. The problem is that DFS does not find all cycles in the graph. It finds a cycle in the graph. So maybe like for this edge, you should have actually removed it because there is some other cycle here, but DFS doesn't actually find that cycle.
Yeah, but that's DFS, right? So DFS...
So we can take that idea for it. So let's come back to that in a second. But yes, you can kind of build on that. But this kind of makes sense, except I haven't told you, like, how do you solve this problem? Because every time you have an edge, how do you know that you're going to get a cycle? You could do DFS to try to find a cycle. But if you did DFS, then it's linear time every time you put an edge. Yeah?
Is it just that, like, if both vertices are like already in the tree, then there must be a cycle if you add that edge between the two vertices?
Exactly. So you have to build a data structure that answers those questions quickly. And it's called a union find data structure. There's a data structure that will answer these questions. So one needs something, there's something called a union find data structure. Have you seen, does anyone know what this is? You've seen the union find data structure? The one that does like path compression and gives this Ackermann inverse thing? Okay, so you've seen it. Okay. We'll see. Maybe next lecture I can actually do this because it is a sort of interesting thing to know. So this becomes a little complicated. It is possible to do. And this is actually, if you put it all together, this is Kruskal's algorithm. It runs in O of m log n. What I want to describe is actually a different algorithm, which I think it's actually more efficient. There are ways of making it more efficient. It avoids sorting all the edges. And it's much more similar, and it uses data structures that you're more familiar with. This is a somewhat funky data structure that you need to use. So, but let's use this idea. So this idea was essentially right, that somehow you want to sort edges and you want to take the cheapest edge at each go. Right? That's kind of the logic that you want to follow. Okay. So given that I started a little bit later and started slowly, I'm not going to take a break today if that's okay, so that we can just finish this topic. Okay. So I want to do this sort of same logic of the cheapest edge, but if you think about the way the picture was drawn, like the cheapest edge would be here. The next cheapest was there. The next cheapest was there. And then these things started getting connected. But observe that what you have at any intermediate stage is a forest. You've got a collection of different trees, and then sometimes you buy an edge that connects them up. And then if you have an edge that sort of connected things that were already connected, like if it was already in the tree, then you wouldn't buy it. So what this does is Kruskal, it maintains a forest. What I want to do is do something more like BFS or DFS, where I maintain one connected tree. Okay? So instead of just buying the cheapest edge, I want to say I've connected this part up. What is the next choice I should do to extend this? Which is exactly how BFS and DFS work. Okay, so the idea is, so let's just start from the beginning. Suppose I buy the cheapest edge. Right? What is the next edge I should buy that is connected to this existing edge? So I've already bought this edge. So think of it like if I'm actually buying things, I put a bunch of workers and I've built that. Now instead of going and buying some edge somewhere else, it makes sense for me to buy something that's connected over there so that I could use my workers over there to build the next one. Yeah? So in this case, it's a weighted graph. So when you say one depth BFS, there are a bunch of edges. There could be many edges here. Maybe some of them are even connected to the same thing. Right? There are lots of these edges. Which edge should I buy? Yeah?
Buy the one with the lowest weight.
Buy the cheapest one amongst those. Which kind of makes sense, right? Because there's some edge that has to get out from here. So buy the cheapest one. Okay. So I promise you, once you understand this argument and you get it, you'll remember MSTs like for the rest of your life. You'll know the algorithm. Even if you don't remember Prim or Kruskal, if I ask you to do it, you'll be like, yeah, just cheapest edge and keep building. Yeah?
If the trees are more than one edge apart, would it be like iteratively trying the combinations of edges?
Which trees? So in this case, you mean in this case?
In the two forests with E1. Like,
Sorry?
In the two forests with E1. I guess maybe if there wasn't just a single link connecting the two forests. Like what it
Over here? Yeah, what about?
Would it change the algorithm, like how we choose the cheapest node? Would it be the cheapest combination of edges?
No, you don't. You will just do one by one. So, okay, so let me explain what I'm going to do here and then you tell me if that makes sense. So we've bought this one edge. So there's one edge E1, and the argument seems to be you look at the cheapest edge that is connected to these, right, which kind of makes sense. So I have E1, E2. And then it would seem like the next thing to do is to look at all the edges going out and just buy the cheapest amongst those. Unless it already connects to something that you have. So what you want to do is you want to see, look at all the edges going out. I buy the cheapest amongst that. Then maybe the next edge is the cheapest amongst the edges that are going out. Okay? So I have to keep track of what is the cheapest edge that is going out of what I have. Does that make sense? Now, what is the natural structure, data structure to do that? You want to always find the minimum, yeah? A heap. Right? So basically you build a heap. And then it's more transparent than like a union find data structure, which is also efficient. But yeah, question?
No, so would it be a heap of all the outgoing edges of your existing, like?
Basically, yeah. So you build a heap of the outgoing edges. Now, a different way to do that is to say, for every vertex that is outside the set that you've collected, you kind of store what is the cheapest edge that gets me to that edge, if it exists. And amongst all those choices, take the cheapest one. Yeah, that was badly phrased. So I'm going to implement it as follows. So there are all these edges going out, but some of these edges may end up leading to the same node. So instead of like putting all of them in the heap, just put the cheapest amongst those in the heap. And the way I can do this is by, like, I maintain a key in a particular way, and I'll write that down. And you'll see that this algorithm is basically just Dijkstra. Because it's looking a lot like shortest paths, except instead of maintaining the shortest path to something, you're just maintaining the cheapest edge that leaves a particular set. So it's actually one line change in Prim's algorithm makes it Dijkstra. But the data structures are exactly the same. Okay, so I'll write this down. So it's like, you've now connected this part. You're going to find the cheapest edge going out. So you could just do a heap of the edges that are leaving, extract the cheapest, and then keep updating the heap. The only thing is when you update the heap, you have to be careful that there could be, you don't want to add edges that are taking you back in the same set. You only want to add edges that are getting out of the set. So you have to maintain a data structure that sort of does that update quickly. So this is just like you have to maintain the right keys and stuff, yeah?
So it could be just like go through all the edges in the actual graph that we have, and if it connects something that is not in the data structure, you pick it. Well, you put it like in a temporal.
In the heap.
Yeah, in the
Heap.
And then you pick the least expensive.
Then you extract from the heap. So you keep inserting and extracting from the heap. The point is to do this in a way so that this extending step is cheap, like runtime wise, like is efficient. You don't want to do a single, you can always do like a DFS on what you have and then do it. But then that would take you like quadratic time.
The algorithm, every time you add a new vertex, you have to add its neighbors to the heap.
Exactly, you have to add its edges to the heap.
And also remove the edges, the new edges that, the edges that connect to the new vertex.
So yeah, so to prevent doing that, so if you did it this way, then you'd have to start deleting stuff from the heap, which is a bit of a pain. So what you do is, when you have all these edges going into this, instead, you know that you only care about the cheapest amongst these edges. So don't even take the more expensive ones. Don't even put them in the heap. That way, you'll kind of save this process. It's almost like this, I think like an amoeba growing, essentially. Right? So there's this, and then you've got a bunch of edges going out. Now, if there was already an edge, if this already went there, you only keep the cheaper one amongst these. Don't keep both of them. So, does that make sense? Now you're saying, how are you going to actually implement this? So you have to use the right heap operations. So there's in the heaps, there's also an update key operation. So you're basically updating keys. So now your keys are not really edges, but vertices. Then objects in your heap are vertices, not edges. And that's going to save you some work. Okay, so this is basically the idea. So at this point, it's time to basically write this down. And this is Prim's algorithm. So I'm just going to write down the algorithm, and then we can discuss. I think at this point it's reasonably clear. I think you all see the picture, and then we can sort of argue on how you would prove this. So let me write this out sort of step by step. So the first step is I'm just going to initialize F, which is my subgraph, to be like the empty set, and a min heap Q with vertices where the key or the priority is infinity. Right? So initially everybody is infinite, like nothing, there are no edges that I've seen. And I'm going to initialize, I'm going to create a set S. So the set S is going to be the vertices that I've collected. F is going to be essentially actually I don't think I even need edge, but F is going to be like the edges that I collect. And Q is the heap, the priority Q. Yeah?
Would the key be part of the heap?
I'm sorry?
Would the key that you're mentioning, is that part of the heap?
The keys?
Yeah.
So think of it as when you have a heap, you have a bunch of objects, and the object has a key.
I see. Okay.
Right? So the heap doesn't extract min over the key
You're
or the
sorting
priority.
keys, though.
Yeah, you're sorting on the keys, but the object is actually the vertex. Right? Yeah. So I'm going to initialize my set S to be some vertex, anything. This could be anything. This is like my starting point. So the nice thing about Prim's algorithm is you get to start wherever you want. You could pick any starting vertex and build from there, whereas Kruskal is just buying edges all over. So you can imagine a real world scenario where you want to buy edges that are sort of from a starting point because you're building infrastructure. You would want to do Prim rather than Kruskal. Okay. Then what I'm going to do is I'm going to do update. So I'm going to update the key in the queue of S to 0. So what I'm doing is I'm basically setting the key of S to be 0. Now in a min heap, you can always do this update key. It takes log n time. This is important. Right, this is the update or decrease key in a min heap. Okay? And then what I'll say is that while my set S is not equal to everything, which is just the same thing as saying that the size of S is less than n. I can also do this when the queue, as long as the queue is not empty. So I do extract min of U, which I'll call U, from the queue and add to S. I'll explain this in just a minute. Add the associated edge to F. Ignore this for now. And then what I do is going to look a lot like DFS. So I did an extract min. I got the min. I'll say for every V in the neighborhood of U, if the priority in the queue of V is more than the cost of the edge UV. So what this means is, think of it as, right now I have some set S. For every other node, I have a priority. For things that are not even connected, the priority is going to be infinite. For this, there's going to be some priority that I have. Now suppose this was U, and I have this edge V. If this edge is cheaper than the existing edge, then I should update the priority of this, update the key of this. Maybe I should say the key, because that's what I'm using, the key. So if there is now a cheaper way of getting to V, other than the edges that you have, then you update key of Q in this V, you make this the cost of UV. I'd say if V is and V is not in S. Yeah?
So the key is the cheapest incoming edge of that vertex.
Cheapest incoming edge from S.
Okay. Like the key in general in a heap would be like for that particular vertex associated to that key, it's the cheapest edge.
No, so it's not necessarily the case. So, okay, I'll answer this in a minute. Let me just go over this. And I'll say make UV associated edge for V. Okay, so let me just walk over this and then I'll explain. So you initialize, your set is in some sense, you haven't collected any edges. You're going to start with a source. You're going to build a heap. Now initially the keys are infinity. What does that mean? It means that from my source, I don't know how to reach anybody. I have no edge that goes from the source to them. So it's all infinity. But I know how to get to the source itself. That's like 0. Now I do my BFS style thing. So I extract min. So when I initially extract the min, I'm going to extract S. Now I'm going to look at all of my neighbors. And I'm going to say, now for all of the neighbors, I have found some way of getting to you. So that becomes the key for those neighbors. But for everybody else, it stays infinity because I don't know how to get to them. So for each of these, I have found some edge that gets to them. So that is the update that I do. Then I do an extract min over all of these. I look at the minimum edge amongst all the edges that are leaving. Then I go back. And so if I find a cheaper edge that gets to you, then I go ahead and update. But if there's some vertex that I have not even seen, I don't even touch, it's still infinity. So it doesn't maintain the cheapest edge for every vertex out there. Right? Like suppose the cheapest edge of the graph is somewhere really far away. I'm not going to actually discover it until I get to it. Until I get to it, right? So eventually I'll get there and then I'll discover it. Does that answer your question? So it's not maintaining the cheapest edge from anywhere, it's maintaining the cheapest edge from the set that I have. So I'll just write this down, just to be clear. Okay? So the Q keys are basically the cheapest edge, the Q keys of V. The cheapest edge to V from S. That's what it's maintaining. Does that make sense? So this is sort of answering your question of how you would implement this efficiently as a data structure. And actually, if you just change this rule over here, you'll end up with Dijkstra. You basically have to take a sum. You basically say that if the key is more than the cost of the edge plus something, then it becomes Dijkstra. It becomes shortest paths. No, so you have to be able to do these operations. You have to be able to do an extract min, and then you have to be able to do an update key. So if you use a min heap, these are log n. Yeah?
What do you mean by the double I make U the associated edge for B?
Okay, so what this is saying is that because in the end, I also want to get not just I want to get the edges that I use to build it. Like in this, it's sort of just extracting vertices one by one. It's not really telling me what edge there is. I'm just keeping track of which edge I use to get to V. So that when I do an extract min, I take that associated edge and I add it to the set.
So that associated would be part of the Q object?
The thing is, you can implement it any which way. You can either have a separate data structure that does it, or you can actually just put it in a Q object. And how you implement depends on what is convenient. But the point is, when you're doing this update, you also update what edge you associate with that. So that when you finally add the associated edge, you have the right edge. This is just like, it's just bookkeeping. So that's why I said, we'll keep it aside. The important thing is to understand the overall data structure operations. So overall this, the running time, if you use a min heap, basically again gives you O of m log n. Because you're going to do one operation for every edge. So it looks like it's the same thing as Kruskal in terms of runtime. But actually, often the heap will be smaller. There's a more fancy heap called a Fibonacci heap. And if you use a Fibonacci heap, you can get the runtime down. You can get it to be something like m plus n log n. But in practice, nobody uses a Fibonacci heap. People will just use a normal min heap, and people run Prim and not Kruskal. Because in Kruskal, you have to, if you have lots of edges, sometimes you just don't want to sort everything. It's easier to just build as you go along. Okay, so this is Prim's algorithm for MST. And this is like, this is like a classic result in algorithms. So it's a good thing to know and see. And again, I'll just, I do want to recall that there are two algorithms. There's Kruskal and Prim. Kruskal intuitively is actually easier to come up with, which is what you all came up with the first go, right? Sort and then just keep picking the minimum edge, but you need something called a union find data structure to implement it, which, maybe depending on how the lectures go, I could take one lecture to do that at some point. It's pretty neat. But it's not a standard data structure that you might see in a course. But really what people will usually do is to implement what's called Prim's algorithm. And Prim's algorithm maintains a min heap. And I will teach Dijkstra maybe in a couple of weeks. Most of you have probably seen Dijkstra. But it's always good to see again. And so you'll see that Dijkstra is pretty much the same algorithm with just one change in this line, where you maintain shortest paths. So here you're basically building like a tree and then sort of extending forward. And so you have these min heap operations. So we do have about 10-ish. Any questions about this first? Is this clear? Yeah.
Do we want to make S be empty at the beginning?
Yeah, maybe, because I think you could because you're doing the extract min over here. You're right. Maybe this little s could be anything. You're right. I guess it would have still been correct the other way, but conceptually this is the right thing to do. That wouldn't have changed anything because you would still extract the S. Like you're just using the S for like some bookkeeping. Yeah. Okay? So Prim's algorithm for MST, minimum spanning trees you can get in m log n time. Using Prim, using Kruskal, you can do both. Okay. One thing that I do want to talk about a little bit is really how do you prove that this is correct? And again, I think by now, hopefully you get it. You get the basic idea. But I just want to write it out a little bit formally so that you see the argument. Okay? Questions? Yeah.
That if 3A, that is the same as the Q?
No, so this is maintaining the set of edges in the minimum spanning tree. The output is really F. So everything else is more like bookkeeping. Like how do you actually get the edges in the minimum spanning tree? So every time you extract min, you have to see which edge did you use to get there. And that you've basically stored because every time you update the key, you're also storing that edge. So, and again, like how you want to store this as a data structure, you could do you could either store it in the heap, you could store it separate from the heap, you could just have a separate table lookup. Just saying that associated for an edges is like just a dictionary. And you can just keep reading from that dictionary, and you keep updating that dictionary. So, you can do it whichever way it makes sense. Yeah? Okay. So let's do a little bit of formalism on proving that this works. And again, the idea is just really like what you've seen earlier. This argument over here, which is consider a spanning subgraph. If you have a cycle, you can remove any edge and it's still a spanning subgraph. And you showed how if you take the cheapest edge that's in an MST, we had an argument on how you could do that. We're just going to apply the same argument again and again and show that Prim is going to work. And so I'll just sort of write out the principles of the greedy algorithm. The principle of the greedy, which is the Prim, the algorithm. Okay, so I'm going to introduce a definition. I'll just say a subset F(E) of edges is extendable if there exists an MST containing the set F. Does that make sense? So extendable just means that if I have these edges, then I can go from here to an MST. And the first argument just says that the minimum edge is extendable. Or any minimum edge, because I can build an MST starting from that. And the whole argument is to say that in Prim's algorithm, this F is always extendable. That's the argument. That is, at every stage, what it has can be extended to an MST. And this is, again, going back to this principle of greedy algorithms, right? That at every stage, the choice it makes is always safe. So it's always making these safe choices. And so the next definition is given an extendable set F of edges and an edge E. E is safe for F if F union E is also extendable. Just sort of basically, this is the principle actually of any MST algorithm. It says that I find a bunch of edges that are safe, so I know that I can build an MST from there. And given a set of safe edges, given an extendable set, find an extendable set, find an edge that's safe, add it, keep recurse. And so if you look at Prim's algorithm, that's also what it's doing, because at every stage it has some F, and then using the extract min, it finds some edge. And if you look at Kruskal's algorithm, it's also doing the same thing, because it's keep adding edges in order unless something happens. So what you argue is that whatever edges it already has is extendable, and the next edge is going to be safe. So this principle of extendable and safe is how all these algorithms work. It's just that they decide to choose different kinds of extendable sets. Okay? And so the argument is how to find a safe edge. And so the way to think about it is that so F may be connected, it might not be connected. So this is F. The argument is that the cheapest edge leaving F is safe for F. Meaning that if I look at all the edges that are going out, I look at the cheapest edge amongst them, the cheapest edge is safe. And why is it safe? Exactly for the same argument that if it was not safe, if there was a different minimum spanning tree, go ahead and add that edge and then delete some other edge. Yeah?
I don't get the notion of safe.
So safe just means that, so you know what extendable is. An edge is safe if I add it to F, then on adding it's still extendable.
Can that not be a question as well?
Yeah, okay, yes?
Can you clarify what you mean by extendable?
Yeah, okay, so extendable means there exists a minimum spanning tree containing those edges. It just means that, okay, so the problem is there are many possible minimum spanning trees. It's not unique. So what Prim is doing in its greedy choices is it's collecting some set of edges. And you have to be able to argue that whatever it's collecting is always correct. So that's what it means to be extendable. It means that it's always correct. Any set of edges is kind of correct if there's always a minimum spanning tree you can build from those edges. That's what extendable means.
But if you're always taking like the minimum from the heap, how is that? How can it be not safe?
It is safe. That's what you need to prove, though. I'm arguing that that minimum is always safe. But these definitions don't say that. This is how you sort of formalize what it means for it to be correct. I'm just writing out the formalism. So the formalism says an extendable set is one such that there exists a minimum spanning tree containing those edges. And a safe one is one where if you add it, it is still extendable. So you always want to maintain an extendable set. And so the argument is that the cheapest edge that is leaving the set is safe. And the proof for this is again the cycle argument, right? So it says that suppose this is the cheapest edge. And suppose this was not part of the minimum spanning tree. So there's some minimum spanning tree that contains all of F because F is extendable. So look at that minimum spanning tree. That minimum spanning tree has to leave F somewhere. So some other edge. So and that will form some cycle because this edge is going to form a cycle. So I could always remove this edge and add this one in. And that's basically the argument. Yeah?
Eventually you will add the cheapest one, so you just might as well add it.
Well, the thing is that both of these could have the same cost. So you could have added either one. So this is where you have to be careful. If the two edges are the same cost, how do you know which is the correct one to add? And what this is saying is it doesn't matter. Both of them are correct. So that's a good question. I'll repeat what I said because you have to ponder on that. Suppose this is the cheapest edge, and it's not part of the minimum spanning tree. We're going to find a different minimum spanning tree that actually contains that edge. How are we going to find that different one? The same argument. We find a minimum spanning tree overall. You add this edge in. Now you know that it's going to form a cycle, forms a cycle. That cycle has to cross this boundary somewhere else because it's a cycle. That other edge cannot be cheaper than this edge. So I could remove that edge instead, and my cost would not increase. And so therefore now I have a new minimum spanning tree. Now suppose that had the same weight as this, then it's fine. Either of those could have been present. Either one could be present, but both of them won't be present necessarily. Someone else had their hand up. I don't know. I thought. Okay, so that's the overall argument. Make sense? I'm not going to write down this proof. Well, not in 2 minutes, certainly. But that's the basic argument, that the cheapest edge leaving is safe, and the argument is, again, this sort of cycle argument, that once it forms a cycle, you could remove any other edge. Okay? All right, so